All right, so quickly, I want to save a little time for us for some other stuff today. Go back to limits a little bit. So let's take a look at this function, piecewise function. So let f of x be defined as x squared plus x plus 1 whenever x is not equal to 1, and is defined as 1 when x equals 1. So what do you think that might end up looking like then? Just in general, what do you think? Okay, so we've got some, okay, that was good. Kurt gave us the universal symbol for, okay, so it's a little bit better if you give it a little, that little sound indicates the point. So, come on, there we go. How about something like that, right? Okay, does that make sense? So we've got this smooth curve defined, and then we've got this 1 point defined at x equals 1 that's off the curve somewhere, okay? So the goal here is, let's find the limit of this piecewise function as x approaches 1. Okay. Well, in the graph, it's easy. What's the answer? 3. Okay. How could we do this maybe without using the graph, though? What's our strategy? Substitution. Okay, but I think I get what you're saying here, but if I substitute x equals 1 into f of x, I get back 1. Okay, so I could do that. But then, so that would be relying on kind of a numerical method, right? Which works, but recall from yesterday, we're kind of trying to shift gears away from graphical and numerical methods into more airtight algebra methods, right? Analytic methods. Okay. So this is like a puzzle. Solution's right in front of you. Okay, put 1 in, by the x you mean put 1 into, I think I'm reading your mind here, you mean put it into that, right? Okay, exactly, we can do that. Okay, but hold on though, it's not, you guys are thinking very practically, which is good, but I'm gonna draw you back in and we need to be mathematically rigorous on this. Okay, what does that mean then? What have we really done here? And this is a big point, so pay close attention. This will be short, but you gotta really focus on this. So what we're saying effectively is, let's pick a different function that's very similar to this one, but it's not the same. Okay, the function we're going to pick, as Katie suggests, is maybe just that guy, right? Instead of f of x equals this piecewise function, let's instead choose a function and call it g of x and have that just equal the top part of the piecewise function, okay? Why is this okay? Justify this somewhere. Why is it okay to do this? Go.
If it's identical except for that one hole in the point all the way down the bottom, then you're going to be getting the same values for every few pellets.
Mm-hmm.
And you'll get a value of what the function is approaching with your new function.
Okay, so there's the key word. And that refers to the limit nature of this, right? Remember, we said limits are only interested in what's happening as the ant approaches the value, in this case 1, not what happens when you get there, right? So if that's true, if the limit's only interested in what the behavior is as you approach it, that's, in this case we can see graphically, well, the ant's approaching that hole right there. And we can see from the graph that it's at a convenient point. But remember, it's always easier to deal with functions where the ant will in fact step where he thinks he's going to step, right? Because it's easy to figure out what the value of the function is on g of x when x is 1. Just plug it in, right? See what I'm getting at? Okay, so effectively what we've done here is we've said, okay, let's trade this crazy function that's got a hole at 1 for a new function that fills in that hole at 1, because we both know, in both cases, we're approaching the same point, but it's really easy to determine what the coordinates are of that point for g of x by substitution. Okay? This technique is, no kidding, this is what we call it in math. This is called a technique where we find two functions that agree at all but one point. Because they agree everywhere except at the one point where f of x contains a hole, right? So this kind of summarizes our strategy. Right? We're going to define g of x as a convenient function that fills in that hole, essentially, doesn't it? That's all it's really doing. And then because all the other x values are the same, we'll just use direct evaluation to find the limit of g of x, because the limits agree. And there's a line here somewhere, right here. This is really important. This may not seem like much, but this is the most important line on the whole page, right there. Because the limit of f of x as x approaches 1 equals the limit of g of x as x approaches 1. Let's just deal with g. Going back to the picture, that purple box, does that make sense? Based on those two functions, would everybody agree that the limit of f of x as x approaches 1 is the very same thing as the limit of g of x as x approaches 1?
Yes.
Okay, good. So that one, you don't have to do any algebra on, right? Because it's a piecewise function. Let's move forward one more step. How about something like this guy? What do you think's going on here? It's actually not. It's not asymptotic.
Because there's the same one in the whole top.
Yeah, so it's a hole, right. Okay, but there is a hole in that function at x equals 1, right? Okay, so we cannot directly evaluate this. Remember, and I want to review this too, remember I gave you kind of my own little device for strategizing how you're going to deal with the limit yesterday. If you try to directly evaluate, there's three things that could happen. What were they? It works. It works, and so you get an answer when you directly evaluate, you're done. There's another thing that could happen. You could get some number, non-zero number divided by 0, which means it explodes. No limit at this point. Limit does not exist, right? Or you could get what? 0 over 0, which is, we're going to call it the indeterminate form. There are others we'll talk about later, but for now 0 over 0 is it. Did everybody agree that's what we get here?
Yeah.
What did that always mean? 0 over 0 means more work. Yeah. So we're going to cheat a little bit. Let's look at some graphs, but we'll do one more after this where we don't look at graphs. So we can see we've got a hole there at x equals 1. What do you suppose, what's the shape of that curve look like? Looks parabolic, doesn't it? Right? Okay, good. So we would expect it maybe to be parabolic, wouldn't we? That would make sense if we divide a cubic polynomial by a linear polynomial. If it divides in evenly, we're going to get back a quadratic, aren't we? Looks like we did, right? Okay, so turns out, yeah, would you agree that is the same parabola with the hole filled in? Same strategy, right? The goal is just how do we get to there, right? How do we get from f of x, which is this, right? Here's f of x. How do we get from f of x to g of x? There's a number of ways you could do this. Suggestions? Okay, yeah, you could. We could factor the x minus 1. Let's try that. Okay, so if we factor out the top, that's a difference of cubes, right? That's a cubed minus b cubed. But how does that work? If we do a cubed minus b cubed, real quick, how does that work? How does that factor? Difference of cubes. Oops, that's not a. There's a. X cubed minus a cubed. Let's do that. What's that factor into?
X minus 8 times x squared plus ax plus a squared.
Good. Yeah. And so that's how that, right, that's how that factors. Okay, that's a pattern. We're going to want to know that pattern. That's if you're not familiar with that, that's one. I'll put some PDFs up with some of that stuff. That's one useful one. Yeah.
What page of the book is this?
It's section 1.3. Yeah, it's kind of near middle end-ish of 1.3, the textbook. Yeah. To get real technical. Okay, so then if we factor that, look what happens. So if we factor that, sure enough, the x minus 1's cancel, and we're left with just that quadratic result, right? Okay. you can go one step deeper with this. You can get almost philosophical with math lots of times. So let's think about this. And this, bear with me on this. Would you agree that when I factor this, the offending factors are the ones, I call them the offending factors, are the ones that cause the indeterminate nature, right? The offending factors are the factors that go to 0 in our limit, as x goes to 1, right? So in this case, would everybody agree that it's the x minus 1 factors in the top and the bottom that caused the 0 over 0 indeterminacy, right? So when we're able to cancel the offending factors, that always results in creating a new function that agrees with the original at all but one point. And in essence, what we do is we fill in the hole, right? So we're just creating a g of x that we can evaluate directly. What a great trick, right? That's the trick we use, right, to resolve the indeterminacy. Okay? And if we keep going, then when we make our substitution, if we let x go to 1, then we plug in and we get 3. Okay? So let's try one more of those, and that's probably, we'll call that good for today. So try this again on your paper. See if you can. Well, you always want to try it first, too. I mean, obviously, I've probably given you one like this, but what would you always want to try first? Substitute. See if it works. It might work. I'll throw some in there where you think they're not going to work, and they do, too, on the homework. You got an answer? Okay. What do we get? -5? Okay. So let's look at y. Now, but before we, before we even look at y, is there even something to drag? No, well, I'll write it. So before we even look at y, would you agree that if I try to evaluate this directly, so the first step is, if I attempt direct evaluation, I do get 0 over 0. Okay, we'll come back to this in the near future, and I'll emphasize this even more, but recall that even in Algebra 2, in Honors Algebra 2, I hammered this pretty good. If you get a rational function, and there's a point where you have a simultaneous 0 of the top and bottom, like we do here. So -3 is a 0 of the numerator and the denominator. What is that guaranteed to be? A whole, right? As opposed to, if I have a 0 of the, like let's say we plug in +2. positive 2 is a 0 over the top, but not the bottom. So what's that going to be? No. If it's a 0 at the top but not the bottom, what's 0 divided by 5 in this case? 0. So that's just a 0 of the function, x-intercept, right? What if we get one that is a 0 of the bottom but not the top? So that's a vertical asymptote every time. Those are always true, right? So now let's just think about this logically before we even jump into the nitty-gritty of the problem here. If we know that we have a rational function with an indeterminate form 0 over 0, you know you have a hole, right? And this is absolutely 100% guaranteed by the math gods. You are going to be able to cancel out the offending factors here. The top must factor, it has to, because you have to be able to cancel out, you have to be able to fill in that hole with another polynomial function, right? Does that make sense? I mean, it just has to be that way, and so you're absolutely guaranteed, before you even start the problem, you already know how it's going to go down. You know that somehow you're going to cancel the x plus 3's to fill in that hole, right? Now, if it were an asymptote, you can't do that, but if it's a hole, you can. All right, so then what's this look like? And I want you to pay special attention here to how I write this down, because this is how you need to write your work. This is a big deal in calculus. Getting ready for the AP test, the work is important. Your work will be graded for half the test. It's all based on your work, okay? And so you can't be, I know sometimes really smart students, they think about an answer and they might not, they just want to get to the answer and they can power through it with their powerful brains, but the work is important. So what would this look like? So this is going to look like, what's my first step going to be? What am I going to do to this rational function? Okay, I'm going to factor the top and bottom, right? Sure.
Can you use longer version?
Well, okay, so you could, but you don't want to, because it's a lot easier just to factor. Yeah, there will be some instances where maybe using like synthetic division would be easier. Using synthetic division might be easier, right? I mean, like, I know what you're getting at. That's really a smart question, because you're thinking, if you know this is a whole, and you know it has to divide out, what if you had some bizarre, you had something bizarre on the top that was not easily factorable, a 7th degree polynomial or something that we're not used to factoring? Yeah, then you would just divide it out synthetically.
Because you can.
Oh, sure, you can, absolutely, yeah.
Well, they do, like, on the AP test, do division subtract from order.
No, they would want you to factor this. And trust me, I mean, this is the first day, so this is pretty new stuff, but within 3 days, you'll just know, I just factored that. I mean, it's just the way you do it. It's easier and quicker to do. So top factors into, you already told me, it's x plus 2 times x minus 3, right? But I have to drag this limit notation with it the whole time, right? Because I'm still taking a limit, right? I'm still evaluating a limit. In math, when we say, finally, the last step, I'll say you take the limit. That means you evaluate it by direct substitution. Yes?
X minus 2, x plus 3.
Oh, whoops, it is. You're right.
Can't we just say limit of x and x equals that?
Can you just say what?
Can't we just say limit of f of x and f of x equals the x minus 2 times x plus 3?
Well, sure. I mean, all I did was I imagine that's up there.
Yeah,
I'm
just
just-
instead of writing limit of x, or should I put it 2, could we just say limit of f of x, and then just put f of x equals that?
No, that's not the way you do it. I mean, this is just kind of generally considered the way people do calculus. It's just sort of they would do it in every calculus college or high school classroom in America. That's what they're doing. That's what a math teacher's going to tell you to do. It ends up being just kind of what you expect.
Is there any benefit to that system over the alternative?
Yeah, there is, because it's consistent with other stuff we'll do when we get into higher level compositions. You always want to do your algebra inside the function. You'd have to do way too much writing if you did it the other way in some cases. So, all right, so then we could, we're just going to cancel those guys, right? And so we end up with, and this is important, this is still a limit, right? We're still taking a limit. So we've got the limit of x minus 2 as x approaches negative 3. So if we called the original function, this rational function f of x, everybody see that that's our new g of x, right? That's the function that filled in the hole, that agrees with the original everywhere but one point. And now finally, the last step is we take the limit, right? We plug in negative 3, and what do we get? Okay.
Wait, so you just keep on writing it with the equal signs, and then you skip down to the bottom line, and just keep on going with equal signs?
Yeah, and that's right, because what does algebra do? Algebra is taking an expression and we're tweaking it step by step. We're morphing it into an answer, right? So every link in this algebra chain is equal. But finally we get to the version that has the answer. Yeah, it's quantified, right? Make sense? Okay, we'll jump into this on Tuesday. We'll jump into this with both feet, and we'll really get into some other kinds, because it's not always rational functions. It could be functions that have some radicals in them, or they could be complex fractions or things. And we have ways to deal with all of those, but they're all very similar. Okay. All right. So thus ends our math for today. What else did I have here? Oh, there's the work for that one. We just did it. Okay.